astronaut on their trip to Mars. And one aspect of reaching Mars is, of course, to use chemical rockets. But to use chemical rockets would entail that astronauts would be exposed to space radiation for maybe a period of several months or a year. So from that perspective, we would like to think about having nuclear rockets because they have a much higher specific impulse. And in that case, a trip to Mars can take only weeks. So that is something to ponder in general. All right, so astronauts, humans, on their endeavor to reach the level, according to Kardashev, of level 1 technological civilization, need to think about if we travel outside the protection of the atmosphere of the Earth, we need to protect our space travelers in that case. Two forms of space radiation are encountered on space mission. One is, as I suggested, related to galactic cosmic rays. These are particles caused by some very far in the past supernova explosions and other high energy events outside the solar system. So that's from outside the solar system, hence they're called galactic cosmic rays. Supernova is when a star runs out of its nuclear fuel, so gravitational energy takes over and it explodes upon itself. And all of us here on Earth, the Earth, all it by itself included, was the result of a known, according to at least our present knowledge, a supernova that happened in the past. So we are really the ashes of a space explosion in our past. There are also other particles that come to us from space, and they're named SEPs. The Galactic Cosmos have an acronym GCRs. The solar energetic particles come to us directly from our sun. And these are also associated with solar flares when the sun's activity is increased with increased magnetic eruptions from the surface of the sun. And they impinge the Earth, and we are protected from them by our atmosphere and also by the Earth's magnetic field that really deflects them from hitting the surface of the Earth, evaporating the atmosphere and evaporating the oceans, like what's happened as best we know on Mars. Mars has lost most of its atmosphere because it doesn't have as strong a magnetic field as the Earth in general. The current spacecraft shield more effectively against the solar particles, which would be electrons and protons, than against the galactic cosmic rays. We'll see why in a moment. We'll calculate the energy of a particle from cosmic rays in general. The particles are either singly charged protons or more highly charged nuclei. They are designated as HZE particles. Please try to remember the acronyms GCR, SEPs, HZE, so that you can read the literature reports and papers and enlarge your knowledge on your own. Z here in HZE is a symbol for a nuclear charge of the particle, the atomic number, in fact. H stands for high, so it's a high Z, and E stands for energy. So HZE is high Z energy particles, and so Z numbers could be iron nuclei. So that's high Z. Why are we interested in high Z? High Z means that they have lots of electrons, and they're also massive in size. Particles encountered in space commonly have enough energy to disrupt the nucleus of target atoms, and these collisions can cause nuclear reactions, which generate new and potentially more damaging particles. And the possible occurrence of nuclear reactions makes the analysis of ionizing radiation collisions somehow difficult, and we need to learn about it. let's talk first about the galactic cosmic radiation. They have been discovered a while ago with balloon flights. People send balloons up into the atmosphere, and they discovered that as they go up higher and higher, the radiation level becomes higher and higher. The knowledge about space radiation originated in 1932. Basically, also that's when the positron was discovered, and they were identified as a product of cosmic ray impacts. And then we discovered the particles that are 200 to 300 times the mass of the electrons. And these are designated as muons and pions. They were discovered a few years later. And by using instrumentation, we were able to even see them reaching the surface of the Earth. And the instrument used in that case is what we call the cloud chamber. I described it earlier, one form of the cloud chamber in the chapter on the high energy on the strong force. The cloud chamber was invented by Mr. Charles Wilson. That's why it's named sometimes the Wilson cloud chamber. And that was invented in 1896. And it allows us to see cosmic radiation, really. So you could see here a cloud chamber. There are two forms. One form uses, that we discussed earlier, uses saturated vapor. So in that case, when radiation goes through it, what we see is a condensation trail, the same as condensation trails or contrails made by airplanes flying in the upper atmosphere when the exhaust meets very cold temperatures. The cloud chamber shown here, or the Wilson cloud chamber, has electrodes basically having a charge on it. And if there is a source of radiation, as the particles move from one part to another, one electrode to the other, you can see their trail. So this is a cosmic particle being shown here is in a cloud chamber. So we know that these particles exist. We know that they interact with the atmosphere of the Earth. The primary cosmic rays nuclei, basically, as we know it, have spent millions of years traveling through the cosmos, reaching the Earth. And we know this because they fall on the Earth isotropically from all directions. They do not have a special source from which they are coming. And during their travel, they go through the space in general. They travel, we know from their attenuation, that they go through a product of the density and the thickness of about 3 grams per centimeter square. So they are attenuated in space through the equivalent of about 3 centimeters of water, or a thickness of iron of about 0.4 centimeters, and a density of iron, as we know, is 8.1 gram per centimeter cube. Nowadays, cosmic radiation, to our best knowledge, is thought to originate from other parts of our Milky Way galaxy. Some of the cosmic rays come to us also from the sun, and these ones coming from the sun have low energies at best, but we are not talking here about kilo electron volts or million electron volts like what comes from radioactivity. We are talking about giga electron volts, 1,000 million electron volts. So they carry a tremendous amount of energy. Well, one reason, of course, is that they are high Z particles, like iron nuclei in general. And I insist that the radiation reaches all parts of the Earth's surface. They're more intense at higher altitude, but are very penetrating and persist even in very deep caves. In fact, some detectors for radiations are built very deep underground in gold mines, like the Homestake gold mine. Sun experiments are built very deep underground so that they basically do not get the effects of those cosmic rays in general. In fact, we know to our best knowledge that our galaxy the Milky Way galaxy has at its center a big black hole, and these could be sources of energy. They are being thought to be the prime sites rays. It is surmised that the black hole exists at the center of our Milky Way galaxy, and these very highly accelerated particles in the vicinity of the black hole interact with some nuclei in the atmosphere here on Earth and produce what we are going to call cosmic ray showers. So let us see what are those cosmic ray showers. So consider that the cosmic particles comes to us from another part of the universe. It penetrates our atmosphere. It's very thin. The air is very thin, but then it becomes thicker. And that cosmic particles, let's say it's an iron, interacts with an atmospheric nucleus. We look at some reactions where atmospheric nuclei interact with cosmic rays. As a result, you'll find that very highly energetic particles disintegrates into many, many, many different particles. Some of them are neutrons, and some of them, like shown N as N here, and it could be a proton also. But primarily cosmic radiations are detected in the form of muons. Muons are particles that are 200 to 300 times the mass of the electrons, and maybe also as pions. They're designated as pions and kaons, a whole panoply or a zoo, if you want to call it, of particles. And as we are sitting here, each one of us on their computer watching the screen, we might be subjected to a cosmic ray shower affecting us here on Earth. So these are occurring all the time, day or night, and they are bombarding our atmosphere. So let us see, do a calculation on how much is the energy of those cosmic ray particles. We know that in the lower atmosphere, some of those cosmic ray showers would have an intensity of 1 million particles in each shower. Each one of them would carry an average energy of 10 million electron volt. And if we suggest that they are attenuated in the atmosphere by a factor of 100 when we measure them at the Earth's surface, then we can get an estimate of the initial energy of those charged particles. So we take the intensity, which is 1 million particles, multiplied by the energy of each particle, 10 million electron volt per particle. Particle and particle cancel out. And then we multiply by the attenuation that they have seen, a factor of 100. That gives me a million electron volt. We turn our electron volt, million electron volt into electron volt, but by multiplying by 1 million. And we find that their energy is 10 to the 15th power electron volts. And if we take 9 out of the 15, you're left with 6. And in that case, 9 would be a giga electron volt or a billion electron volt. You could see here, it's not million anymore. Remember that the energy is 1 giga, 1 million giga electron volt in that case. So it's quite a very large energy that those particles carry in that case. Actually, this would be million electron volt. 1 million electron volt here, that should be corrected. That would be 1 giga electron volt. So I'll give you an assignment where we should correct that number here. This is 1 million electron volt. 1 million electron volt is 1 giga electron volt. In that case, the cosmic radiation exposes us to lots of different particles. And in fact, in the same way that we have the table of the elements and we have the chart of the nuclides, all the isotopes, there is also a table of the subatomic particles that we know of. And this is within the realm of cosmic physics in general, cosmic radiation. But we can look at some of those particles here. and they are divided into families. We have the hadrons. They comprise the baryons and the mesons. This is one of the charged particles, in that case, the pions, is designated as pi plus. And the electric charge is a charge of the 1 electron charge, but the mass in million electron volt units is 139. So if you say it's 100, and you say that the mass of the electron is 0.51 million electron volts, so they have basically 200 times the electron mass. Those pions do not remain as pions. They decay into other products, a mu mesons in that case, and a anti-neutrino, and its antiparticle has the same way as the electron has a positron as an antiparticle. The pi plus pion has also a pi minus antiparticles. So this is called mesons, again, in reference to cosmic radiation. The baryons are strongly interacting particles that are also called fermions, include what we have been dealing with more frequently, the proton mass, the neutron, which has no charge, but has a mass of 939 million electron volt. But look at all the hadrons that in the table of elementary particles. We have the lambda hyperon, the sigma plus hyperon, the sigma 0 hyperon, sigma minus hyperon, and so on. In the mesons, which comprise primarily those cosmic radiation, as I suggested, we have the pions, and we have the omega particles and the eta particles. Other than the hadrons, we have also the elementary particles, and elementary particles comprise what we know about the photon, the graviton, that is some kind of a theoretical particles. It is still a topic of research, and the muons. So now notice that the pions are cosmic radiation as classified as mesons, whereas the muons also, which are cosmic radiation, are classified as elementary particles. The classification also, okay, in elementary particles, we have the photon, and we have our famous electron and its antimatter, the positron. So in our classes, we have dealt only with a part of the whole. People call it actually is a zoo of particles. In that case, these are a list of subatomic particles that people involved in high energy research are dealing with. In addition to generating the cosmic radiation or the cosmic ray showers, in the cosmic ray showers, the protons and neutrons produced can interact with the elements in the atmosphere. Remember that what we breathe as air is 70% nitrogen and only maybe 15% oxygen. So what we breathe in our atmosphere is primarily nitrogen, in contrast to another planet like Venus or Mars. Their atmosphere are primarily carbon dioxide. So in our nitrogen and in our atmosphere, the neutrons generated by those cosmic ray showers can interact with the nitrogen-14 isotope. And lo and behold, you find that it turns into the carbon-14 isotope, and a proton is emitted in the reaction. You'll find that neutrons are also captured in deuterons, and they produce a very, very tiny amount of tritium, the isotope of hydrogen that's radioactive in the atmosphere, and gamma photons are emitted. But carbon-14 is a very interesting isotope because, of course, our life on Earth depends on carbon. So as an organism, whether it's a plant or an animal, as long as it is alive, it is incorporating carbon in its body, and part of that carbon is carbon-14, which is radioactive. And as the individual, the plant or the human die, they stop incorporating the carbon in their body. So in that case, the amount of carbon-14 decays, and as it decays, we can emit beta particles. In that case, we can tell the age of any biological material, and this is the basis of what's called carbon dating. We are gonna analyze carbon dating very quickly here, because in anthropology, it helps us determine the age of very ancient objects. You help the knowledge that we have already acquired in terms of activity units. Remember, the Curie is 3.7 10 to the 10th transformations per second, or becquerel. And from that, we can use it for carbon dating. It's a methodology used, knowing that carbon-14, now remember that each one of us has some carbon-14 in our body. It has a half-life of 5,730 years. Only living plants and animals continue to incorporate carbon-14, and they stop incorporating it after death. So in that case, it is possible to determine the age of archaeological artifacts. For instance, if you find an old site of humans and they had a fire, you can get a piece of charcoal, and in that case, carbon dating can tell us what is the age of that settlement of in ancient times, or the age of a mummy in, say, a pharaoh's tomb, and so on. So let us derive the equation that allows us to determine the age of an archaeological artifact. So if you do archaeology in the future or help an archaeologist, then that would be your way of determining it. So in that case, we know that the law of radioactive decay for activity is initial activity, e to the minus the natural logarithm of 2 divided into the half-life of the isotope. Remember, for carbon-14, carbon-14 decays with a half-life of 5,730 years. So if you substitute the half-life here at 5,000 years, you will get your time of course, in years. Well, but it's not interesting for us just to determine the activity after a time t. This is an inverse problem in mathematical physics. We want to determine the value of t, knowing how much radioactivity has decayed over time. So if we solve, if we take the natural logarithm of both sides, after bringing the here the a prime infinity to the left-hand side, you'll find that t becomes the minus the half-life divided into the natural logarithm of 2 multiplied into the log of a prime over at prime. Let's take an example. If say the half-life of the equilibrium radioactivity is 15, we know that is a typical number for the radioactive decay of carbon-14. The half-life 5,730 years. Remember the negative sign here. The natural logarithm of 2 is 0.6931. Then when you measure the activity in the sample that you have and substitute it here, oh, you get the time, the inverse value of mathematical physics, in that case, of the archaeological object in years. So you'll be invited basically to, given some data, to determine if you substitute the measured value of the sample specific activity from equation 9 into that equation 8, you can determine the geological time in years. I'll try to give you a problem just to get some idea about the computation. It's a very simple one. It's an inverse problem of mathematical physics. Some radioactive isotopes other than carbon-14 produced in the atmosphere from the neutron bombardment that from cosmic ray showers is listed here. We suggested, of course, carbon-14, and the activity density in the lower atmosphere is 4 disintegrations per minute per meter cube. We also produce tritium. We mentioned that by the interaction of a neutron from cosmic radiation with deuterium, but beryllium-7 is produced. It decays very rapidly. Beryllium-10 can last for millions of years. Sodium-222, sodium-22, silicon-32, phosphorus-32, phosphorus-33, sulfur-35, and chlorine-36. Some of them have short half-life, days, but some of them have millions of years half-life. So whatever is produced remains for a long time in our atmosphere in general. All right, now, so this is an interesting use of the unit that we call the activity in archaeology, and determine the age of archaeological objects within the range of the 5,000 years half-life. If you want to determine geological lives, like the age of a rock that was formed a long time ago, then you use the same techniques, but for the decay of other radioisotopes like uranium and thorium and so on. All right, so, but we are interested in the effects of radiation on our instruments in space. We need to shield, for instance, our communication devices against space radiation and cosmic rays. So in that case, the activity is not sufficient for us. We need to think about the radiation absorbed dose unit. And we define the rad as the unit for in the CGS system of units, centimeter gram second. And we define the gray as being 100 rad in the SI system of units. And in that case, the rad is the amount of energy or dose of radiation absorbed by an object. And it was designed or used in to honor Mr. Louis Gray. He was a radiation pioneer. He lived from 1905 to 1965. So in that case, when we calculate the effects of radiation in terms of the dose rate in rads, because remember that when we deal with living matter, in biological matter, we use the REM, and we'll use that later when we start talking about doses to astronauts but if it's a matter of materials absorbing radiation, we use the radiation absorbed dose by definition. So in that case, you find that we have different sources of radiation. The external sources definitely now, if we break it down, are caused to us, to any material, in fact, the doses from external and internal sources of radiation. And we are going to concentrate here on natural radiation. Cosmic ray at sea level, the ionizing component gives us basically 28 millirad per year per person. The neutrons 0.7. We have terrestrial radiation. The terrestrial radiation comes in from the decay products of the uranium-238 and the thorium-232 decay chain. So that gives us 50 millirad per person per year. Notice here that at the top of the atmosphere, the cosmic ray radiation is 30 millirad per year, but then if you go to 20,000 feet, it's higher because those cosmic rays have interacted now with the atmosphere and generated all those cosmic ray particles that we have mentioned. In addition, of course, we are subject to internal radiation in our body. We mentioned the carbon-14 gives us 1 millirad per person per year, but we have more of it as potassium-40, 0.01% of natural potassium, and it's an electrolyte. Without it, we cannot have our heart or our muscles function. That's 20 times what you get from carbon-14. We have some contribution of 1 millirad per person per year of radium-226 and radium-228, some of tritium, and the average for the total body is about 100 millirad per person per year. Again, I insist that we are, or remind you that we are continuously being bombarded with also solar neutrinos, but solar neutrinos are not counted in the estimation of the dose, because those neutrinos are very weakly interacting particles that can go from one side of the Earth to the other or they can come in from the other side of the Earth and basically hit us even during our sleep without interacting with the whole Earth in general. These penetrate matter so easily that their intensity on the shadow side of the Earth is still about 90% of the on the sun side. Extraterrestrial radiation has a component which consists of strange particles resulting also from catastrophic high energy collision. Now, how does radiation affect living organism or biological system in general? And the effect on living organisms, of course, is measured in that case by what we call the dose equivalent or the equivalent dose, because different types of radiation affects different organs in different way. But in essence, the HZE particle, the high Z energy particles, affect our DNA. We know that our cells contain a nucleus. The nucleus has in it the this is a DNA helix. The helix itself contains genes, and if we get an X-ray, the X-ray as electromagnetic radiation may go through the DNA in the chromosomes inside the cell without much interaction. But if you have cosmic radiation now, a heavy ion particle can go through the DNA of the chromosome and cause great damage, as shown in that diagram. So cosmic ray particles would cause a tremendous amount of damage compared, say, just to an X-ray or a gamma photon. So we have to be careful in the exposure that our astronauts are subject to when they are in, say, the space station or on a trip to Mars or in a future base on Mars or on the moon. And this is an actual picture that's not pie in the sky of the chromosomes of some astronaut, unspecified, I don't know who it was, but this are the chromosomes inside the cell. They were simply separated from each other here. And you could see damage to some of those chromosomes. You could see that's, of course, this is chromosome number 2. Following a space flight, you could see how badly damaged it is here. And there was another form of damage that those pieces that are cut from the chromosomes can reinsert themselves into another chromosome, as shown here. It's called an insertion. And in that case, that chromosome would have different properties. And of course, it means that we really have to shield our astronauts against space radiation in general. How do we shield against radiation? Space is a very harsh radiation environment. It's harsh not just on humans, but also on the instrumentations of the spaceships. And you'll find that aluminum used in aerospace in building those spaceships, aluminum because it has a low density, so it's light in weight. Titanium also somehow is useful. It's easy to launch them into space. Typically, it's about 0.5 centimeter, 5 millimeter in thickness, and but it provides very little reduction in the number of energetic ionizing particles. The shielding itself provides secondary particles. Like when the cosmic rays interact with aluminum, they produce other particles that themselves cause also an additional hazard. And I remind you now that if you have living matter, the way that we measure radiation is not the rad anymore, but the REM, or the radiation equivalent man. And when you take the rad that we showed in the previous table multiplied by the quality factor, or the radiation quality factor, you get the radiation equivalent man here. That is in the CGS system of units. In the SI system, we have the sievert. So you have to remember that 1 rem is 1 centisievert, and we are going to use the centisievert unit, meaning it's also the rem. They're used interchangeably. And here it is. Here is a way to assess now the effects of radiation on space travel. If you think about the International Space Station, this is the dose equivalent, and in 1,000 of a sievert, millisievert per day received by the astronauts remaining in the International Space Station for a stay of about 6 months. So it was measured in April, May, June, July, August, September. And you can read it here as a dose equivalent of about, let's say, 0.5 or 0.45 millisievert per day. So the longer the stay, the higher the accumulated dose. However, now if you are going to think about a trip to Mars or a base on Mars, if astronauts just remain in Mars orbit, look, that 0.45 now becomes 1.3 millisievert per day received by the astronaut for an average trip of 6 months on Mars. So you could see the ratio here, 1.3 to 0.4, though it's a much larger dose of radiation for a 6 month stay of the astronauts. And we notice, of course, that the radiation effect on the astronauts, either on a base on the Moon, the Mars, or in the International Space Station, is in addition to effects on the human body. So any space travel to our the Moon or any other planet, Mars is the first one under consideration, should be, the astronauts should be protected against space radiation. And if a base is built on the Moon or on Mars, they have to be protected. So you cannot just put them in those cylindrical enclosures that are shown in diagrams of building bases on the Moon or Mars. You have to think about protecting the astronauts. So it's a better way of thinking is to basically build those enclosures underground, or maybe on the side of hills in general, but not being exposed to space radiation in general. All right, now what are the space radiation sources? We suggested that galactic cosmic X-rays come from explosions maybe of supernovae that happened millions of years ago. But we have the solar particle events. These are particles that are generated from our sun, and they are trapped in the Earth's magnetic field in what we call the Van Allen radiation belts. The types of space radiation that we have to worry about in terms of the flux of particles per second per square centimeter are the ones coming from the sun. It's the closest celestial object to the Earth, and the solar wind is trapped in the Earth's magnetic field, and as it reaches the Earth, it can generate the Aurora Australis and the Aurora and basically the northern lights and the southern lights. So you'll find either protons or electrons in general. The electrons can be trapped in the Van Allen belts or the Earth's magnetic fields, and they are also can be increased to a certain degree when we get solar storms. And solar storms are notorious when the sun goes through its 11-year activity cycle. You know that the magnetic field of the sun reverses from north to south every 11 years. At some point, the intensity becomes almost of radiation from the sun becomes almost zero, and then it starts increasing. We are in the 25th measured solar cycle, and it is increasing lately. You can get solar flares that also can generate protons, and this is most of the radiation that we really get on Earth from our nearest star, the sun. Galactic cosmic X-rays have a very low flux, but nevertheless, they carry quite a bit of energy, as we have seen in the 1 giga electron volt of energy. Let's talk a little bit more about the galactic cosmic radiation. What is their composition? You'll find that their composition is can be very low Z elements like hydrogen here in the atomic number. That's a relative abundance, but some of them could be magnesium, silicon, neon, or even iron. When you have iron, you have a high HZE isotope, so it's not just a matter of the abundance, but also the amount of energy that they carry in that case. Galactic cosmos are composed of many elements, but the halide nuclei dominate. The hydrogen abundance peaks at about 10 times larger than the helium and 10,000 times more than the iron peak, like what you see in the diagram. If you put it on a logarithmic scale, the cosmic high Z energy particles are primarily hydrogen, helium, carbon, and then with a lower abundance, the iron that can carry the 1 giga electron volt of energy. So this is the galactic cosmic rays. Now, how about the solar charged particles that come to us from our star, the sun? They occur primarily when the sun is active, and the activity of the sun is displayed in what basically is a sun magnetic sun flares. You could see that reactions in the surface of the corona on the surface of the sun are affected by magnetic fields, and the charged particles, as you know, rotate around the magnetic field lines, and these are displayed in the solar flares. Some interesting fact that is not very well known about the solar flares is that they occur always in pairs. You could see here one spot and another spot, and that is because the magnetic field from the Earth acts like a rubber band. So you find that the magnetic field goes up and then comes down again with the charged particles rotating around it. So we see the sunspots as pairs of sunspots. This is a picture taken of the sun by NASA. Another event that happens from the sun is basically solar flares. So along those magnetic field lines, you'll find that those particles in the magnetic field now can reach a height above the sun's surface, and they can be ejected. And as they are ejected, particularly when the sun is very active over this 11 years cycle, the actual period becomes, of course, 22 years, they can reach the Earth. And when they reach the Earth, they can not just affect our satellites and our space stations, but they can also affect our communication systems, as we'll see it in another chapter. What happens in that case is what we call CMEs. These are coronal mass ejections. These are huge bubbles of gas threaded with magnetic field lines that can be ejected from the sun, almost like a sprinkler. When you have water coming out of the sprinkler, the sun is rotating, so it reaches the Earth like a sprinkler. It could or could not hit the Earth. And if it hits the Earth, we have very powerful implications about our communication system that we'll discuss later on. Those coronal mass ejection can be huge in size, and this is a picture, I think, from NASA or NOAA. That's NOAA, National Oceanic and Space Administration here. They can reach a height of about, is a thickness of 28 Earths. Luckily, every time that happens, the Earth most of the time escapes being hit by it. But there have been events like the Carrington event that we'll mention in a moment in another chapter that affected communication on Earth, and our communication systems must be really designed to be able to withstand those coronal mass ejections. So here is some kind of schematic of the sun. It is not to scale, obviously. The Earth here would be just a little dot. The Earth's magnetic field, as the solar wind hits the Earth, or the coronal mass ejection hits the Earth's magnetic field traps the particles, because the charged particles rotate around the magnetic field lines according to what we have learned earlier from the Lorentz or the Joule equation. And as they rotate, they can come in at the north, like a big, some kind of ellipse here on the north part of the Earth, and another lives at the southern part of the Earth. But most of those charged particles are ejected back into space. And remember that the Earth's magnetic field is caused by the existence of radioactivity under our feet. So life on Earth is really existing in between radioactivity under our feet that creates a dynamo of the Earth, creating the magnetic field that protects us against too much of a good thing, the radiation from the sun. But some of the radiation from the sun is also necessary for life and photosynthesis and plants' life on Earth. So we owe our life to two nuclear processes, the solar radiation coming from above us and radiation under our feet. So luckily for life on Earth to have emerged is the protection that the Earth's magnetic field are protecting us against solar mass ejections and the solar wind. Some anomalies happen on Earth that people do not understand, and they give it some kind of interpretation that may be very wrong. And this is an anomaly that happens because of the fact that the Earth's axis of rotation here is not the same as the axis of the radiation belts. So as the radiation belts surround the Earth's surface shown here, you'll find that there is near the coast of South America a spot where the Earth's magnetic field becomes very close to the surface of the Earth, and that arises from the asymmetry of the axis of rotation of the Earth and its magnetic field axis. So you find that near the coast of South America here, like in Brazil in particular, you'll find that the radiation field is higher than in other parts of the Earth. This is the coast of South America shown here. And then people interpret the magnetic events as being alien ships and so on. It appears as magnetic phenomena like in the atmosphere. So this is the dose rate from the Mir 18 space station, showing that South Atlantic anomaly just east of the Brazilian coastline. So the incidence of unexplained aerial phenomena, particularly in South America, can be related definitely to that anomaly of this Earth's magnetic field in general. As I suggested here, if you go to space, the charged particles can be part of the interstellar gas that has different concentrations, the matter density in the solar neighborhood, the kinetic temperature of the gases in protons, and the temperature of the grains of particles in the basically in the sky, if you want to call it. Electron bombardment is something to worry about, as well as proton bombardments and even dust grain bombardments in the design of our spacecraft and our communication system. The name for it is that we harden our electronics in our spaceships and our communication systems in satellites, the GPS system, and so on. From the radiation in space, you can get heating, you can get permanent damage, you get mass loss through ablation heating, or you can get ionizations in general. What if we find our way to Mars? Well, we are thinking about going to Mars. So this is a radiation field that we can think about. This is the dose equivalent. Remember, we know the unit of the dose equivalent as a sievert in the SI system, or the rem in the CGS system of units. You find here that the 6-month stay, transit or travel to Mars would give the astronaut the equivalent of, let's say here, this is the logarithmic scale, so that's about 300 millisieverts total absorbed dose. If you have astronauts staying for 6 months on the International Space Station, it's only 100. So here it is, we have a factor of, let us 3 times the dose rate for a 6-month stay in the International Space Station compared to what you get for a trip to Mars that takes 6 months. Hence the emphasis here that if you want really to minimize the dose of radiation to our future astronauts going to Mars, we need to get a shorter travel period, not 6 months. We need to reduce it to weeks. And in that case, you have to use a high specific impulse type of a rocket. And that has to be, well, the only choice in that case would be a nuclear rocket. So if you go and work for Mr. Elon Musk, give him some good advice. The people at NASA are smart enough to understand that. So they're thinking about more or less a trip to a base on the moon before thinking about a base on Mars. For comparison, this is what you get from a CT scan, computed tomography, because these are X-rays, that's only 10. The space station, you get 100 over a 6-month period. Well, a single scan gives you 10 RAM, 10 millisievert of radiation dose. And the annual average that we shouldn't worry about is in the range of about 5, maybe annual from all sources in general. And at sea level, we cannot avoid getting that level of radiation about let's say 0.3 or 0.4 millisievert at sea level. If you go to a place like Denver, Colorado, then you lose the protection of the atmosphere and the dose rate would be higher. And of course, travel by airplanes also subjects us to higher levels of radiation. So you could see here that radiation is not a matter of just nuclear power generation or nuclear medicine, but it has to do with our future ambition of extending life to the rest of our solar system and maybe to the rest of the universe. I'll stop here for a few moments. If there are any questions, I'll answer them in the chat room. Otherwise, I will move to another chapter. All right, we'll go to another chapter. We have time. So related again to radiation today. So we go to share the screen. So we looked at cosmic and space radiation, and what I would like to talk about related to it that we already mentioned somehow is what is the effect of space radiation on our nuclear installation. So you may find yourself working in the utility business, and then you have to think about protecting your transformers and your power equipment on a nuclear installation in general. So let us go and have the effect of solar storms. They are a fact of life. We cannot avoid them on nuclear and electrical installation in general. This is of interest to all engineers that will be working in the nuclear field as well as in the electrical field in general. These solar flares can affect really events on Earth. And one aspect of them is a blackout that happened on August 14, 2003, and in the eastern and central United States. You could see here, and Canada, in fact. If you look here, this is a Great Lake, that is Illinois would be here. And this is the area on the west coast, Canada here, and the east coast on a normal night. One of the events in 1972, 2003, August 14, a solar event affected the power grid in Quebec, Canada. Basically, it turned off all the circuit breakers, and you could see a blackout ensued as a result. You could see the less lights in that case because of a event. In that case, that is the 2003. It happened also in 1972, in 1989 in Quebec, Canada. 6 million people had to lose power. There have been more serious events that happened as a result of the solar flare. You could see a solar flare here and the magnetic field of the sun, like a rubber band leaking out of the corona or the surface of the sun, with charged particles rotating around it, exiting from one point and coming to another. And I pointed out to you that an observation that many people miss is that when solar flares occur, they occur in pairs. So that's a pair of them showing us how the magnetic field rises and then comes back to the surface of the sun. This one here would have one that goes up and down. Each one of those is usually a pair, and this is a picture of a solar flares by NASA. Now, in the case of the mass ejection, then there is an interesting effect that happened in that case, in that I mentioned the idea of the water sprinkler. If this is the sun and this is our tiny Earth here, and the sun ejects some of the charged particles, they occur as some kind of a sprinkler, and sometimes they can hit the surface of the Earth and sometimes they cannot hit the surface of the Earth. This is an event that happened in 2017, just 4 years ago, and NASA and has spaceships basically that are monitoring space weather in the same way that we are measuring the weather here on Earth. And they measure the neutron intensity, the X-ray intensity, as I'll show you in a moment. In fact, you can go on the internet and watch the space weather in the same way as you watch the weather on Earth. Another more recent event is on the 22nd of February, 2018. And this is radial velocity and plasma density from a solar, again, mass ejection, coronal mass ejection. And it hit the Earth, this one, on May 27, 2017, and then back again on February 17, 2018. So this is not too far in the past, and it can happen any day. Satellites by NASA monitor those events, and in different cities, Boulder, Colorado, for instance, you could see that this is what's called the K Index. And at that date in particular, you could see that the solar radiation, the neutron flux came in to be very high. And this is the coordinates in universal time. So that was May 22nd, that was May 28th. I'll show you maybe if I have time a way of monitoring the space weather all by yourself, but it does happen. They call this a Planetary K Index, and the K sub P index is shown by measurements from satellites. That is a May 28, 2017 effect. Now, what we are interested in, of course, we are not cosmologists, but we are interested in the possible effects of those events on electrical and nuclear power plants. It is believed that a direct coronal mass ejection, CME, remember CME is coronal mass ejection, occurred on July 23rd, 2012, and it affected the GPS system. That's very serious because now planes and ships do not depend really on using astrolabes to determine their position on the surface of the Earth. It's now all GPS. So if the GPS system or global positioning system is affected, you'll find planes falling off the sky. And according to a study by the National Academy of Sciences, the total economic impact could exceed not $2 billion, but $2 trillion, 20 times greater than the costs of Hurricane Katrina. Remember, Hurricane Katrina caused quite a bit of damage, but that's 1/20th the damage that can happen from the coronal mass ejection that would hit the Earth. It would fry many of the transformers and those transformers at power stations need to be replaced, and they can take years to repair. So imagine a very strong coronal mass ejection. Well, that would turn us back into the Stone Age to a certain degree. And this is also bears a discussion when people talk about electromagnetic pulses and the use of nuclear weapons intentionally to cause basically a damage to the electronic equipment if it's exploded in the atmosphere above a large extent, maybe over the continental United States. Physicist Pete Riley published a paper on the probability of occurrence of extreme space weather events. It calculated that the odds of a solar storm strong enough to disrupt our lives in the next 10 years is 12%. So it can happen, well, but humans are smart and can basically recover from these calamities in general. This is how the solar sunspots or the activity of the fusion reactions on the surface of the sun cause the solar cycle. And these are actual measurements, as you could see here near the peak of one of the cycles. It decreases, it almost reaches very low when we don't see any sunspots, but then it starts increasing again. And this is a predicted value by NASA that it will reach a peak. That is, I think, the event 25. No, actually, this is an earlier one, 2011. It goes up to a maximum, then goes down with a cycle of 11 years. Okay, what do we worry about as engineers in terms of those solar storms? This is a list that I could write here about what can happen. First, radio communications can fade out. We can lose our radio communications. You'll find an interesting event, the Aurora Borealis and the Aurora Australis would be because of the trapped charged particles in the Earth's magnetic field. The northern lights is the Aurora Borealis and the southern lights, Aurora Australis. These are fun to watch, but of course, this is also radiation emitted from the interaction of the solar particles with the nitrogen atoms and oxygen atoms in the atmosphere. This is fun to watch. In fact, if you, when it happens, find your way north to Michigan maybe or Wisconsin, and at night you can watch it at night. It's a wonderful sight to see. However, it can cause disruptions other than the radio communications and GPS in the electrical grid power lines. It can disrupt radio transmission. It becomes what we call a geomagnetic storm. It's also called sometimes ionospheric storm that happens in the ionosphere. And it is a great radiation hazard to astronauts in the International Space Station or in a trip maybe in the future to Mars. The immediate effect could be that it literally fries the transformers at power plants, nuclear or otherwise. But of course, if you destroy the power components of a nuclear power plants, and you can get a core meltdown, and the effects could be much more serious than, say, if you destroy the transformer on a core power plants. In either case, replacing those transformers can take years. They don't keep transformers, the manufacturers don't keep transformers available for replacement because they're so expensive and the events themselves are not very common. This is a satellite kind of measurements of the real-time solar storm density, speed, and temperature by NASA. So space weather is monitored in the same way as climatic weather in general. The data are listed by NOAA as well as NASA. So you could see here, they have an estimate of the solar flare risk, the solar X-rays being normal or abnormal, and the geomagnetic forecast also being forecasted in the same way that we forecast the weather, because the implications can be tremendous. This is pictures of the occurrence of the Aurora Borealis in a geomagnetic storm that hit the Earth. The charged particles were, as I suggested, trapped by the Earth's magnetic field. That was on May 27, 2017. And it affected airlines communications because of the effects on the GPS system. And in fact, at that date, British Airways canceled all their flights. And there were power outages in Karachi, Pakistan, as a result of that event. Notice that it is not quite even. It can extend to a certain degree closer to the equator in some parts of the world. Here, for instance, this Aurora Borealis would have been watched in or seen in Canada and the northern United States. So they do occur. Some of them hit the Earth and some do not hit the Earth. That's another geomagnetic storm that happened on May 27, 2017. And look here, if you were in northern Wisconsin, you would have been able to watch part of it. And even though the magnetic storm affected the Aurora Borealis here, happened more like north of the, well, towards Canada primarily, but you'll find that power outages happened as far down as here in Illinois by the utility Ameren and at Kenosha, Wisconsin, according to NOAA. Those events were not very serious events, so they caused only local power outages in general. Solar storms affecting the Earth can progress in 3 stages. First, of course, what moves at the speed of light are electromagnetic radiation. So you find X-rays and ultraviolet. They ionize the Earth's upper atmosphere, and in that case, they interfere with radio communications. Then you get fast protons and electron charged particles, and they can also affect, in that case, the astronauts on the Earth's orbit. So we need to shield those astronauts effectively to protect them against the solar radiation. And a coronal mass ejection now follows because this is a mass. It's not like electromagnetic radiation. It takes time for the coronal mass ejection to reach the Earth. So the X-rays gives us an advance warning so that we can generate at least some kind of defenses in general. They take several days to reach the Earth's atmosphere. And when a coronal mass ejection hits the Earth's atmosphere, the solar particles that can interact with the Earth's magnetic field and produce very, very powerful electromagnetic fluctuations, much more than what, say, lightning would be causing in general. Coronal mass ejections are a very serious matter, and some people try to show how, like depict the shape of a storm. Here is our wonderful little Earth here being subject to a literally a storm interacting with the Earth's magnetic field. Without the Earth's magnetic field, those coronal mass ejections would fry the surface of the Earth, burn the atmosphere, evaporate the water, and lose it to outer space. Unfortunately, this is the situation that we are learning about happened to Mars. Mars does not have a magnetic field. It doesn't have that molten core from radioactivity that the Earth is basically lucky to have. So in that case, again, a depiction of how the Earth's magnetic field really preserves life on Earth. Many depictions are shown. The Earth's magnetic field lines simply carry the charged particles away from the Earth without their boiling our oceans and our atmosphere away from us. This is the extent of the Aurora Borealis. In January 2012, we could see here that it appears as some kind of a semi-circle. Now, you don't see the Aurora Borealis during daylight, obviously, but you see it at night. So that's the half part of the Earth that is night, and this is the half part that is the day. And in fact, it takes the shape almost of a semicircle. It doesn't have to be totally closed. Again, this is the lighted part of the Earth. The sun would be on this side. This is the shadow parts, and of course, it can reach very high altitude. The more serious the Aurora Borealis, the lower it can be seen at the lower latitudes in general. That is an event that happened in January 212. And this is what you see. This is a gentleman standing there watching the beautiful northern lights, or the Aurora Borealis, in Norway. Norway, as you know, is a very high latitude country, and that is in the 2012 events, a picture from NOAA in general. This is the one of the satellites, the GOES satellite, 5 minutes average proton flux measurement coming from the one of those events. So we have space weather being watched in general. We worry a bit about coronal mass ejection, and we worry about nuclear power plants, obviously, more than we worry about coal or other power plants. Because if you destroy the electrical components of a nuclear power plant, and you do not have a chance to continue cooling the decay heat, as you mentioned earlier, you have to cool the power plant for at least 24 or 48 hours from the decay products. We call that the decay heat generation. You can cause a meltdown, and accidents like the 3 Mile Islands, Chernobyl, as well as Fukushima could occur in general. The geomagnetic kind of mass ejection can cause also an induced currents, and the consequence of that strong current, much stronger than what you get in lightning events, is to drive transformer cores into saturation. And if that causes significant heating from the stray flux, increases the volts ampere reactive power losses, depress the system voltages, and can in fact damage a transformer. I'll show you a picture of a damaged transformer in that case. Another interesting aspect is what we call multiple contingency instant under certain operating conditions can jeopardize the integrity of the bulk electrical systems in North America, Canada, and the United States. And in 1989, there was a very famous event that happened. The one that I've shown you caused the blackout. Let's look at exactly what happened there. On March 10, 1989, one of those geomagnetic storms affected northern Canada in matters of days. And according to a description by NASA, quote, on Friday, March 10, 1989, astronomers witnessed a powerful explosion on the sun. Within minutes, tangled magnetic forces on the sun had reached a billion-ton cloud of gas. Billion ton. It was like the energy of thousands of nuclear bombs exploding at the same time. The storm cloud rushed out from the sun straight toward the Earth at 1,000,000 miles per hour. The solar flare that accompanied the outburst immediately caused shortwave radio interference, including the jamming of radio signals from Radio Free Europe, I think, yes, into Russia. It was thought that the signals had been jammed by the Kremlin. They thought that was some kind of intentional, and it was only the sun acting up in general. On March 1989, 7 static voltage events compensator or Hydro-Quebec high voltage transmission network were affected. The transmission lines have been affected, and it happens more in Canada, as you could see, because the latitude of Canada is further towards the north in general. Communication satellites can be damaged. Some communication satellites stumbled out of control in space for several hours. Space Shuttle Discovery sensor on one of the tanks applying hydrogen to a fuel cell was showing unusually high pressures. And in 1989, we also had some global effects, so that's a very common effect in general. Earlier events happened that were much more serious than what we have gotten frequently. And the most famous event is what's called the Carrington event. At this time, the people were using telegraphs. So people who were using the telegraphs basically had their instrumentation catch fire. And it has been named the Carrington event after the British astronomer Richard Carrington. During the Carrington event, northern lights were reported as far south as Cuba and Honolulu, while southern lights were seen as far as Santiago, Chile. The flares were so powerful that people in the northeastern USA could read newspaper print just from the light of the Aurora Borealis. The geomagnetic disturbance was strong enough that USA telegraph operators reported sparks leaping from their equipment. Imagine how strong the current that was generated was with some setting equipment fires. And that event is very famous, known as the Carrington event. There are other events that happened in 1921 and so on. I'll let you read the history of it. In 2011, we had a solar storm on February 16th, and that is better documented than 2012. X-class flares did occur. Double bursts occurred on March 6, 2012, and that was associated with those solar flares. These visual pictures I remind you again of the trivia that solar flares occur in pairs, and the reason for the pairs again is that the magnetic field lines on the sun acts like rubber bands, so they stretch out. The charged particles rotate around them, and what we see is the point at which the magnetic field exits the corona or the surface of the sun and then gets back in again. That is a picture from NOAA. This shows us the association of those flares with the emission of X-rays. This is a satellites looking at the X-rays, and this is satellite looking at the visual part of the spectrum. And the detection, again, the 5-minute solar X-ray flux, that X-ray flux reaches the Earth before the charged particles themselves. So it gives us some kind of a nice warning about maybe protecting our equipment in general. What we worry about as engineers is the effect on modern electrical systems. And we worry about the cascade failure, because once you get some transformer stations to trip to like circuit breakers, when they get a very high current, shown like here, then they trip, but then they are usually replaced by other lines taking over the tripped line, but then a cascade failure happen when all of them start failing one after the other. And as I suggested, the damage to the electrical equipment can be serious. You could see here that gentleman, that engineers there standing in front of a transformer at the power station, March 13, 1989. You could see here the fire that occurred in the transformer and the damage, basically rubble all over the place from the heating up of the transformer. And more detail, you could see here the transformer fire that happened in the transformers. If you don't have those transformers, you cannot export power generated from a power station, whether it's nuclear or non-nuclear. Nuclear becomes more, of course, serious than the non-nuclear events in general. So what do we do in society? We have basically to be prepared for any of those events, because their effect on the United States grid system can be monumental. Some people call it monumental. That event in 1921 caused the damage to 350 high voltage transformers and power outages affecting 130 million Americans. If you are 360 or 350 million, almost 1/3 of the population would be affected by those loss of power. Imagine not having your refrigerator or your oven or a light in your home available to you because the power is totally lost. And again, it has to do with the capability of our Earth to protect us through radioactivity in its center, generating our wonderful shield around the Earth. You could see here these are the radiation belts of the Earth. They're named after Mr. Van Allen. We call them the Van Allen radiation belts. They're not just one belt. They take the shape of a torus here. And you could see there are different levels. When solar storms occur, they extend their distance. Our communication satellites and the International Space Stations are positioned outside those radiation belts. But you could see that they can shrink and extend in their extent around the Earth. And it was interesting to listen to some astronauts' interviews, and they didn't know that when they are being launched into the International Space Station that is outside the Van Allen belts, they didn't know that they had to go through the Van Allen belts, and they would receive a significant dose of radiation going out and being returned back to Earth in general. So when we launch future spaceships, we have to think about the instrumentation, definitely not launch spaceships at the time of a solar flares. There are what is called high impact, low frequency HILF events. Some storms can be potentially catastrophic. They're not very predictable in either their frequency, how often they happen, or their strengths. And they are grouped with electromagnetic pulse events. They might be caused by the detonation of nuclear devices in the upper atmosphere by an adversary, hoping to take down the high voltage grid by causing what's called an electromagnetic pulse. That was a topic of concern when the relations with North Korea were some kind of tense in the past, but now they have settled down. Along the protection against it, there is a project that basically have put aside some transformers. I call it the REC-X project. The Electrical Power Research Institute, EPRI, and the Department of Homeland Security work on a project to design prototype recovery transformers in general. All right, that brings us back to the effects of the electromagnetic pulse threat to humans from the nuclear war. If you explode a nuclear device in the higher atmosphere, lots of electrons are generated, and so that they basically mimic the same effect as the coronal mass ejection. The neutrons, even the neutrons emitted, apparently are proposed to decay into protons and electrons themselves. So they add to the intensity of electron formation, and they can cause the same effect as, say, a serious solar flare hitting the Earth. And so in that case, in fact, the military supposedly have designed devices that can generate an electromagnetic pulse preferentially to one that would not. They don't tell us what's typical of the design. I'd assume that it would be a neutron generating device, so it would be more like a fusion device, generates lots of neutrons, and neutrons decay into electrons and positrons. The positrons generate X-ray, gamma rays, and then X-rays. Let me read that paragraph. A study conducted in the United States during the late 1980s reported that a high-yield device exploded about 500 kilometers above the ground can generate an electromagnetic pulse, which is the same as what happens in a strike of lightning, in fact, of the order of 50,000 or 50 kilovolts over a radius of 2,500 kilometers around the point of burst, which would be collected by an exposed conductor. There was a movie by Tom Cruise, I think, where aliens were attacking the Earth, and an electromagnetic pulse fried all the electronic equipment on cars, so you couldn't even start the car. Such an attack would not cause any blast or thermal effects on the ground below, but it can produce a massive breakdown in the communication system. Some people are some kind of suggest that this is a humane way of using nuclear devices because it does not really kill humans directly. but it would kill them through starvation and returning back a whole society back to no use of electrical generation and all our electronic and life-making devices, heating homes, for instance. That turned us back into the Stone Age and can cause death and starvation. It is certain that most of the land communication networks and military command control links will be affected, and it will undetermine our capability to retaliate. This, in fact, is the most powerful incentive for a preemptive attack. Another stupid suggestion by people who advocate the use of nuclear weapons in war, in international conflicts. And a high altitude exoatmospheric explosion may not kill a bird on the ground. So they say, oh, that's humane. It is not humane from the effects that will happen in general. Tests have been conducted by the United States on that generation of electromagnetic pulses, and several events happened. In fact, one of them was called the Starfish Prime. That was a thermonuclear device about 1 megaton in energy, and it would have produced 5,000 nanotesla per minute field strengths, magnetic field strengths, and this basically it damaged can damage 365 large transformers in the power grid, and you find that 40% of the United States population would be without electrical power for as long as 4 to 10 years. Imagine that, due to loss of large transformers that would have to be custom built in other countries if power was not available for the 2 USA plants that are able to make these transformers. So it can be a life-destroying event. This is a picture, in fact, of that Starfish Prime test on July 80 in the upper atmosphere. It was part of what was called Operation Fishbowl. It was detonated in the Pacific on an artificial island, in fact, called Johnston Island. It used basically dragged sand to construct an airline landing strip, and all the way from that Johnston Island in the middle of the Pacific, it was observed at Honolulu, the capital of Hawaii, at night about 1,897 miles away. And it damaged 300 street lights, but it turned basically the night sky into almost daylight. So these ideas of effects of solar effects, so mass ejection on electrical installation of Earth is of great importance for people who would be having careers in the nuclear power or power industry in general. A testimony before the United States Congress by Dr. Lowell Wood. He's a famous astronomer, and he tells us, quote, most fortunately, these tests took place over Johnston Island in the mid-Pacific rather on the Nevada test site, or electromagnetic pulse would still be indelibly imprinted in the minds of the citizenry of the Western US, as well as in the history books. As it was, significant damage was done to both civilian and military electrical systems throughout the Hawaiian Islands, over 800 miles away from ground zero. The origin and nature of this damage was successfully obscured at the time, aided by its mysterious character and the essentially incredible truth. The incredible truth here is that nuclear war is, the best way to win a nuclear war is not to play it. And it tells us that our installations would be extremely vulnerable to an attack where one opponent preempts the war by using an electromagnetic pulse in imitation to what can happen to us from the sun. Just for the fun of it, I'm going to go back to our portal, to the web page, and you can have fun yourself. Let me see here. You can connect to that sunspot number site, and you could see that's the latest by basically that's we are 2022 right now. You could see that the solar activity peaked in 2014, and maybe it will peak again in 2025 right here. This is a prediction, and this is a solar cycle, and this is a plot of the solar flares that are actually observed on the surface on the sun. This is what is happening daily, and that is the predictions by NASA, and basically the satellite is called the SILSO satellite. You can go to another watch of the space. You can have fun watching the the space weather. This is the let me see if I can get that link. That's a galactic cosmic rays measured on a daily basis. You could see that lately there has been an increase here in the number of neutrons coming up from the sun, but it's decreasing back again. And in the case of solar flares, you find that these numbers would increase. This is called the Oulu neutron detector. I think it's in Finland. That's a space weather. And you can basically go to the NASA spot. This is the Space Weather Services here. This is a flare class. And in one of the diagrams that I've showed you in one of those ejections, there was a peak here. So it tells us here the sun is fine. So we shouldn't worry about our satellites or GPS. But in the case of a solar flare, you'll find that if the level here reaches that point, then basically that is an alarm system. That's a solar X-ray flux. The X-rays coming to us from the sun, and they will warn us about the mass ejection, because then another satellite measures the proton flux. You could see it's almost constant. So our sun is calm, and it is not reaching the high level here. Sometime on around July, maybe a few days ago, the geomagnetic activity increased, but it came down back again, and we survived it. All right, so let's see here. Go back to our notes, and I will maybe come back to the notes themselves. We covered two interesting chapters today. One on, of course, space radiation, and the other one on how they affect our nuclear power plants and other electrical installations in general, including power lines from any form of electrical production, and the hazard of the electromagnetic pulse that you may have read about. All right, so we still have some time here that are worthwhile to cover some other radiation phenomenon that I mentioned in the previous lectures, and that would be the process of the radiation hormazes. And it is a controversial topic, but it is interesting by itself. So we cover today the cosmic and space radiation. And all right, let me see here. Cosmic space radiation and the solar storm effects on nuclear and electrical installation. If we go to the topic of health physics and effects of radiation, we did mention the radiation hormazes. So what is radiation hormazes? Radiation hormazes is an interesting topic that suggests that very low doses of radiation do not cause much harm. In fact, they kind of encourage the immune system to defend the body and reconstruct any damage that is caused by radiation. So let's see what it is all about and reach some conclusion about whatever knowledge we learn about it. Biochemistry during the 1920s was called physiological chemistry. Now we call it biochemistry. And basically, some people, Sazam and Ehrlich, noticed that large concentration of oak bark extract inhibited fungal growth. But in low doses, they lead to the paradoxical effect of stimulating fungal growth. Fungi will grow with very low doses, and they die with very high doses in general. So they published the results in a journal, and they basically started using the word Hormazes. And Hormazes now describes the stimulation of low doses of agents that are harmful or lethal at high doses. Hormazes comes from the word hormone, of course, which are proteins that are part of our biological system. When we consider it from the perspective of ionizing radiation, the topic raises heated debates. I warn you that this is a very controversial topic, but it will give us some idea about what is the effect of low doses of radiation. A vocal minority of radiation biologists support it, and basically that leads to an unsettled controversy. What is the pharmacological history? At some point, doctors will go with a poison, strychnine, in their bags, and they prescribed it to people in low doses, and they consider it as a stimulating tonic for elderly patients. Only in high doses was strychnine kind of considered a harmful poison. In history, the Russian monk Rasputin, who was in the court of Catherine the Great in Russia, there were conspiracies there. They liked at the point not to use polonium-210 to poison their opponents, like what's happening today, but they would poison their enemies with arsenic. So Mr. Rasputin, the monk, is rumored to not being affected by a large dose of arsenic because he expected his opponents to try to poison him. So he took small doses of arsenic in general. You'll find that biological observations, if you have a lack of oxygen, affects the body at too low a concentration below 5%. However, a moderate oxygen deficiency stimulates red blood cells generation. So common substances like nicotine, caffeine, alcohol, and water, water too, in fact, have mild effects in low doses, but they become toxic and even deadly at large doses. Nicotine, in fact, it's used as an insecticide. It kills insects when used in high doses in general. Pharmacologists tested the toxicity of drugs by giving groups of test subjects like bacteria or mice, and that measured the LD50, and that is, or LD90. That's a lethal dose that kills 90% of the population within a 30 time. It turns out that low doses of medications can enhance the process of the body building defenses, and is not affected by large doses of the chemical in that case. Radiation hormones comes in with the topic of radiation, and I'll let you read the material. And I mentioned to you that we learned about the deleterious effects of radiation from the survivors of the bombing of Hiroshima and Nagasaki, but also from the radium girls who used their, who had radium-226 ingested into their body by painting the dials of luminous swatches at night. So we learned some bad experience about this. We have a very bad experience in the history of radiation. At some point, it was thought that it has beneficial effect. So that Revigator dispenser was dispensing basically water from a container that contains uranium ore, and it was given claims that it can have beneficial effects. Radithor is a bottle sold in 1918 containing radium-226 and radium-228. It was considered again as a snake oil that you could buy it in the form of pills. That you had even a device called the radium emanator that would be releasing the radon gas, which is toxic. The radium itself is toxic. You can also buy radium earth. So at the beginning of the history of radiation, it was misused by snake oil salesmen. They even had people inject thorium into their body with suggesting that it has nice effects on A kerosene lamp uses a thorium mantle. Thorium, as you know, is radioactive, and people used Fiesta ceramic glass glazing agents, and these are really uranium salts. So those material, those plates would be radioactive, and some coloring agents was used in what's called depression glass. People collect those nice looking, nice colored glasses, but they have radioactivity. Those dial painting young girls were painting really the dials of those clocks and getting radium-226 in their body, but it was used also as for buttons. It was used for as a cream, beauty cream for ladies, and that was part of the misuse of radiation in general. So radiation was misused, radio here, vanishing cream, and so on. And when we didn't know about its effect, now we know better about it. Why are we talking about this? We are talking about this because of what's called the linear low dose effect. And in terms of radiation, the linear nose threshold risk dose relationship is adopted to extrapolate to the effects of the low doses of radiation. Interesting enough, you find that the excess relative toxicity is lower at low doses of radiation, and some people suggest that this means that the low doses of radiation are not harmful, but they are beneficial. So below 50 rem, we extrapolate the effects at high doses of radiation that curve out one. This is what we call the linear nose threshold relationship. Some people suggest that low doses of radiation here would have a beneficial effect. They even go lower in the curve here than the known effects. As professional dealing with radiation, because we don't know about the effect of low doses of radiation, we don't know that in fact they are beneficial by enhancing the immune system. So we are bound to adopt the linear nose threshold effect. There is no threshold here, and basically this is the common knowledge about radiation today. All right, so some people even talk about radiation preconditioning, increasing the life of some test animals in general. So in terms of Hormazes, if you want to read about it and learn more about it, the consensus from the atomic bomb survivor studies is that, quote, in the presence of available data, it is neither sound statistical interpretation nor prudent risk evaluation to take the view that the risk should be considered as zero in some low dose range due to lack of statistical significance when restricting attention to this range. So as long as we don't know more about the effects of low doses of radiation, the principle of using radiation is what we call the ALARA principle, as low as reasonably achievable, and we have to adopt it as the consensus in people using radiation in their professions. And I'll stop at this and remain in the chat room for any questions.